Admiral Blandy, General Kepner, and Admiral Parsons survey the damage in the target array. Shown here is the Japanese battleship Nagato, which flooded and capsized 5 days after the blast. Seven and a half hours after the explosion, the aircraft carrier Saratoga, grand old fighting lady, sank as a result of heavy underwater hull damage. It must be remembered that the primary purpose of the Bikini experiments was to secure precise technical information which will be used to determine necessary changes in the design and construction of all military equipment and especially Navy vessels required to maintain your Navy at maximum effectiveness. We must be fully prepared to protect our national security promptly and effectively in the event that we are attacked. We must defend ourselves against this new and elemental force or be destroyed by it. This is Crossroads.
July 1945, Alamogordo, New Mexico. Watch the first atomic detonation in history. Operation Trinity. The long series of nuclear tests is underway. July 1946, Operation Crossroads. Bikini Atoll in the mid-Pacific. The war over, scientists and military personnel busy themselves setting up a target of ships for the first peacetime test of the atomic bomb. High-ranking military personnel and civilian observers watch the able shot. 19 kilotons burst 516 feet above the surface of the lagoon. Damage to the target array is assessed and preparations are underway for the Baker shot. The bomb, similar in type to the Able test, is located in an airtight caisson beneath the surface of this tropical lagoon. With all preparations made, Baker shot occurs on schedule. Many impressive and startling effects are observed on this shot, including the first appearance of a base surge, seen here enveloping the target ships. April 1948, Eniwetok Atoll in the Pacific. Our third nuclear test program gets underway. Operation Sandstone. 3 weapons, fired on 200-foot towers, with batteries of scientific instruments to record results. As at Bikini, drone planes are used here. Giant planes, heavily instrumented but without crews, take off to fly through the heart of each atomic cloud, to collect samples of that cloud for detailed radiochemical analysis. Three times the sound and fury of atomic detonations shatter the Pacific dawn. 3 times a scientific laboratory is created to study previously unattainable effects of high temperatures and pressures. But What did we learn from these detonations? What were we trying to prove? Why did we expend this almost priceless nuclear material and these thousands of man-hours of labor? Let the men of Los Alamos give us the answers.
We returned to the Hill from the sandstone tests with new and important information. Information that would enable us to make a sizable contribution to the generally rising curve of man's knowledge of atomic weapons. Information that would help us tackle basic problems involved in high explosive systems, pit designs, core arrangements, initiators. Information that would enable us to increase the small percentage of active material that actually burns during fission. The more efficient use of fissionable material has been and continues to be one of our main objectives. For it is the fissile material itself, whether uranium-235 or plutonium, that is the expensive, the elaborately complicated material to produce. The nuclear material is the heart of all our attempts to make bombs economically feasible. At Trinity in 1945, we proved a self-sustaining reaction could become an explosive force, and that the implosion principle was sound. We had a starting point. The drops on Japan were strictly a war measure. At Hiroshima, we tried the gun principle and also used uranium for the first time. The Nagasaki weapon was an implosion type using plutonium. Little or no controlled experimentation was possible. Thus, little data was obtained which furthered the progress of weapon design. As a result of the Japan detonations, the effects from an atomic explosion became of prime concern to the armed forces. Thus, Crossroads using an implosion system. At Crossroads, since we were mainly interested in testing naval materiel, little data was obtained from the Able and Baker shots on weapon development. However, significant effects knowledge was obtained. Stateside laboratory research, in the meantime, developed new weapons for the sandstone tests. At Sandstone, we were once again able to tackle the big problem, more efficient use of fissile material. Here, we were able to utilize uranium-235 in an implosion-type weapon. As time went on, we had increased our knowledge of weapon design and had, therefore, increased yield per kilogram of active material. This is where we stood by the end of Sandstone. It is equally obvious that testing at a proving ground is to be a permanent feature of our work. So a proof test division, known as J Division, is organized. Dr. Alvin C. Graves is selected to head this division, a unit with the specific job of testing weapons. By autumn of '48, a test program is framed. This calls for experimentation of new weapon designs with the objective of again moving our knowledge curve upward to a more effective level. Once more, we propose to better yield per kilogram invested. Greenhouse may take us a long way in the direction of smaller weapons. For the first time, deliverability in terms of size and weight is expected to make its mark in improved weapon design. Greenhouse will also give us direction as to what road to follow in the development of a thermonuclear weapon. These are the main objectives in the weapon development field.
And so Operation Greenhouse gets underway, with Eniwetok designated as headquarters island for the Pacific Proving Ground. Engebi, Runnet, and Eberiru are the shot islands. During late 1950 and early 1951, work progresses in the islands. Towers are built. Recording stations are constructed. Coaxial cables for the shot towers are laid. Myriads of instruments and intricate wiring hookups are checked and double-checked. Finally, everything is ready for the biggest job in nuclear testing, the job of obtaining exact information about the detonation itself. The builders are through, and the scientists take over the story.
Those of us from the scientific task group are here essentially to confirm or disprove theoretical calculations, to learn what is not always possible to prove in a conventional laboratory. To learn more about the atom bomb, we divide our testing into two major areas: diagnostic testing and effects testing. More specifically, diagnostic tests are an extensive examination of the phenomena occurring during the initial phases of the explosion. Effects tests study the external manifestations of the explosion, the effects of the weapon. To gain an intimate understanding of interior weapon behavior, three kinds of diagnostic measurements are made. These are the time it takes to start the nuclear reaction, transit time; the rate at which the chain reaction multiplies, alpha measurement; and measurements of the total energy released in the nuclear reaction, yield. Most of the diagnostic data is available only during the early microseconds of the nuclear reaction, and extensive instrumentation is required for each detonation. Transit time data, which gives information on the HE system, is cabled down to a recording station and measured by sweep oscilloscopes. Transit time instruments are wired into the same circuit that triggers the detonators of the weapon. Because they are activated by the same impulse, they can literally measure the duration of the implosion, or the time necessary to condense the nuclear material to criticality. Transit time is the interval, then, between the impulse and the appearance of the first gamma ray, which signals the beginning of the fission process. The oscilloscopes are extensively photographed during their microseconds of operation, since transit time is an important index of implosion efficiency and offers a good check of weapon design. The second phase of diagnostic experimentation, giving information on the internal workings of the core, is the alpha measurement. One way to obtain this data is to locate an ionization chamber adjacent to the weapon itself. Other ionization chambers, located at ground level, detect later stages of the alpha phenomena. Measurements of alpha give valuable information on the multiplying qualities of the fissionable assembly. The multiplication rate is vital. It tells us of the growth of fissions in a given length of time. If we are to have more efficient atomic weapons, we must increase the rate at which fissions multiply. As radiations from the fissions are detected, a signal is sent down the coaxial cable to a recording station. The rate of increase of signal strength is recorded by some of the fastest recording equipment in existence today. In addition to the transit time and alpha diagnostic experiments, we have several methods of detecting the success of new weapon designs in terms of yield. Yield is the determination of the total energy released by the nuclear material undergoing fission. This energy is usually expressed in kilotons, 1 kiloton being the force released in 1,000 tons of high explosive. One means of measuring yield is to attach filter traps to drone aircraft and send them into the core of the atomic cloud immediately after the blast. Nuclear ashes or samples of the residue material saturating the cloud are collected in the traps for radiochemical analysis to determine the total number of fissions that have occurred. Since we know the yield per fission and measure the total number of fissions, the yield of the bomb can be computed. The SNAP sampler, a device new to atomic testing, is another way of collecting debris for radiochemical analysis. Samplers of the air type and samplers of the ground type are arranged in a semicircle close to the base of the tower. In addition to these methods of collecting samples of fission fragments, Greenhouse will test rockets for the first time to see if they are practical as sample collectors. The rockets will be fired just prior to shot time. They will travel in a long arc and pass through the cloud at approximately 5,000 feet. It is hoped that on the pass-through, they will collect samples in much the same way as drone aircraft. Another measure of yield is made with high-speed still and motion picture cameras, which record the rate of growth of the fireball. The more energy developed in the reaction, the faster it expands. To repeat, the diagnostic experiments are concerned with the behavior and phenomena of the weapon itself.
Shot number 1, dog. The objectives of the test of the Howe weapon were to prove a weapon of higher yield and efficiency than currently stockpiled. The predicted increase of efficiency made possible by the Type D pit was confirmed. Shot number 2, easy. The objective of the test was to prove a lighter and smaller weapon with acceptable efficiency. The feasibility of obtaining acceptable efficiencies with lighter and smaller weapons was confirmed, and thereby future weapons design was advanced. Shot number 3, George. A step was taken along the path to thermonuclear weapons by the achievement of a fusion reaction . Shot number 4, item. A successful booster reaction proved the feasibility of increasing fission yield by a limited fusion reaction and gave more impetus to the development of booster weapons. Fission weapons proof tested. Physics experiments run on thermonuclear reactions. Military and civil defense knowledge immeasurably increased. This was the accomplishment at Runit, at Engebi, at Eberiru in the spring of 1951. Once more, the Pacific Proving Ground has proved its value, but the job is far from complete. Each test series leads inevitably to new developments requiring still more tests, more frequent than are practical at distant Eniwetok, where logistic problems make it difficult to run more than one test a year. We need a site much closer to home, a site in the continental United States. But where?
For a long time, as a matter of fact, ever since Trinity, men from Los Alamos had been eyeing the great barren stretches of the Southwest. This region, for the most part, fits the bill. Isolated from centers of population, with favorable winds, with the necessary consistency of soil and formation of earth strata below. And so beyond the World War II training base, to the north of an early-day Nevada stage stop called Indian Springs, 65 miles north and west of Las Vegas, an atomic range was established. A test site of over 400 square miles of flatbed valleys, mingled with mountains of solid rock, whose veins once colored history with gold and silver. A range remote from civilization, isolated, forgotten as the names of the men who once made their fortunes here. In the pre-dawn hours of January 1951, this long deserted countryside came once more into international focus with Operation Ranger. The test of 5 atomic bombs. 5 successful airdrops that saved the weapons research program months of time, considerable money, and helped Los Alamos prove the radical new idea of small atomic bombs. Soon after Ranger, another use of the Nevada test site was apparent. This was a chance for the military to get more information in a shorter space of time on the effects of atomic weapons. Vital facts. For what good are atomic weapons without full knowledge of what they can really do and how we can be protected against their effects?
Thus, Operation Buster was born. In the fall of 1951, the combined Operation Buster Jangle was held at the Nevada Proving Ground. Five weapons in Operation Buster, 1 on a 100-foot tower and 4 air drops. A tent city, Camp Desert Rock, was activated and occupied by observers from all the services. arriving here from all corners of the Earth to participate in an atomic maneuver. Here they receive extensive indoctrination by experts from the Armed Forces Special Weapons Project in the expected phenomena of the detonation, and by Camp Desert Rock personnel on the assumed tactical maneuver. Early on shot morning, they load into trucks and buses for the long trip to the target area. In the target area, last-minute orientation talks are given, and the observers prepare themselves to watch an atomic detonation from the closest point that personnel have ever been during nuclear tests. Following the detonation, the troops move forward to the ground zero area to inspect the effects of the bomb. Since the Ranger shots were experimental devices only, this was the first stockpile weapon to be detonated within the continental limits. Operation Jangle, immediately following Buster, was our first test of surface and underground atomic detonations, designed to study military effects of these types of bursts. Jangle number 1, the surface shot, heavily instrumented to study energy coupling in the Earth itself. This low-lying cloud is hot with radioactivity trapped in Earth particles thrown out by the force of the explosion. In a little while, ground monitors mark off the outer limits of personnel re-entry into the blast site. In the fringes and interior of the crater itself, the spot that once was ground zero, there are soil specimens of great value if they can be collected before their short-lived radioactivity dies. Remote-controlled Army weasels, drone weasels, are warming up for this collecting job. A compact television camera mounted on the front of each weasel will inspect the terrain as they go and relay the picture back to their guiding control station. Scoops on the front of one drone will gouge out and bring back surface samples of the crater dirt. A drill rig mounted on the back of the other weasel will bore down and secure cores, which will tell the story of subsurface radioactivity. Now the push is on for Jangle 2, the underground detonation. Like the surface shot, this will be a 1-kiloton gadget, but this time it will be detonated 17 feet beneath the surface of the Nevada soil. Very extensive military effects tests will be run with this detonation. Dummy buildings with superimposed loads to represent upper floors, and underground structures, such as fuel storage tanks, water systems under hydrostatic pressure, gas mains, and electrical mains have been constructed to gain realistic data on ground shock and cratering action. Inside the control point, members of the Military Effects Test Group supervise the detonation.
5, 4, 3, 2, 1, 0.
After the detonation, test structures are studied, and the many scientific and military personnel involved return to their home bases to evaluate the results of the operation. After the 7 shots of Buster Jangle are complete, the test area lies dormant, waiting, ever ready for future tests. Our proving grounds, Eniwetok and Nevada, stand ready to aid the scientists and the military in their job of preparedness, of developing weapons and doctrine for any possible future atomic war.
Well, another ZI atomic test is history now. Past history for the record books and live history for future planning. It was a double-header test like Buster Jangle and Tumbler Snapper, covering both weapon development and civil and military effects. And in some ways, it was our biggest research job so far. The preparation job was big too. Many hundreds of tons of material and months of intense planning and labor by skilled personnel were the ingredients, poured into a gigantic test tube, our Nevada proving grounds. In the spring of 1953, the mixture boiled up in a series of 11 atomic detonations. Operation Upshot Knothole. The residue or end product of the reaction was knowledge, some of it in a yes or no form, immediately useful, and some of it requiring detailed analysis. The funnel into our Nevada test tube was the same old road up from Las Vegas. Nearly 80 miles of standard desert road which carries very little traffic when the proving grounds are quiet. Indian Springs was still primarily an Air Force support station for atomic test operations. The Desert Rock Troop encampment was in the same old place off to the left, after we turned off Highway 95. Inside the check gate and Mercury were living and technical areas and the field headquarters of the main test organization, a joint AEC and Department of Defense activity. From Mercury, the road goes roughly northward. It cuts through one range of hills. On across the valley of Frenchman Flat, then heads up into a notch in a second range. In this notch is the CP, the control point, the real nerve center and communications hub of the test site. This was the test manager's forward headquarters for the series, and primarily the center of operations for the weapons development program, Upshot. Looking out from the control point, an observer can see both of the major blast areas. Frenchman Flat, a dry lake bed, is still visible back in the valley we just crossed, though the actual ground zero point can't be seen. Yucca Flat lies on northward, in the next valley beyond the control point. 9 of Upshot Knothole's 11 shots were fired out here on Yucca between March 17th and June 4th. These 9, 7 tower shots and 2 airdrops, were the AEC's weapon development tests. While such tests are not the main point of this film, their trend, the goals they're aimed at, are ultimately of great importance to the military services. So since these tests are primarily the concern of Los Alamos Scientific Laboratories, we turn to Los Alamos for an outline of the concepts and the objectives involved.
As usual, we're up to our necks, unraveling what happened in the last tests and getting ready for the next ones. Now, this weapon development business. We've been getting together some material for brief orientation talks. I want to emphasize that the amount of discussion given each shot is no indication of its actual importance. In fact, I may have to say at least about some of the most important shots. Shot number 2 had for its source of energy a boosted fission device. It was part of a development that we think will eventually give us a weapon of approximately 30 inches in diameter. 3,000 to 4,000 pounds weight and a yield in the neighborhood of 500 kilotons, around 35 times that of the Hiroshima bomb. The next development shots were 3 and 5. Shot number 4, it was the first airdrop on Upshot and was detonated at approximately 6,000 feet, the highest burst of any gadget we've ever fired. So, once over lightly at least, that winds up the story of Operation Upshot Knotholes weapon development program.
But outside of any discussion, outside of the laboratories, out on the Nevada proving ground itself, there was a great deal more to consider than the basic ideas back of the upshot firings. There was the same old job, complex and vitally necessary, of diagnosing the actual performance of gadgets being tested. Gadgets designed by Los Alamos and by Project Whitney of the University of California Radiation Laboratory. It's an old story, in a sense, to those of us in the services who have watched and assisted the preparation of previous tests. But that doesn't alter its prime value. To get the inside dope on the behavior of any experimental fission device, the scientists always want at least the answer to one classical three-headed question. What was the alpha rate, the transit time, and the yield? And yield alone is computed and cross-checked in many ways. Probably most accurately by radiochemical analysis of cloud material collected by the sampling planes, and by ultra-high-speed photography of fireball growth. Another Nevada activity of the AEC was its civil effects program of tests originated by various non-military federal agencies. For example, 2 typical frame houses were exposed to the first blast of the series for the Federal Civil Defense Administration. Some 50 civilian automobiles were included in this test. Several types of family and community bomb shelters were also tried out. The blast from the 16-kiloton shot hits the house at 3,500 feet, around 3/4 of a mile, almost total destruction. The other house at 1.5 miles showed only moderately heavy damage. These visually spectacular tests were only one portion of a big program which included extensive dosimeter and radiation research and important biomedical and genetic studies by some of the country's top scientists. The second major phase of the 1953 series, military effects tests, was, from the service point of view, the main feature of the show. All early planning and coordination of these tests was handled by the Directorate of Weapons Effects Tests, set up for this purpose by Field Command, Armed Forces Special Weapons Project. In the operational phase, personnel of this directorate were integrated into the main test organization. There, they continued to be responsible for all military tests and for the important military support given to the AEC's programs. Such support, for example, as the Air Weather Service forecasts, on which are based the fire or no fire decisions for each shot. The bulk of the huge knothole program was carried out on Frenchman Flat, though some military tests were run on the weapon development shots up on Yucca. Number 9 on 8 May was the first knothole shot, an airdrop of a 26-kiloton weapon. All military tests on Frenchman Flat were originally built around this shot. The relatively high burst height, 2,400 feet, was a compromise to fit many tests, rather than to inflict maximum central damage. Shot 10, 25 May, proof-tested another delivery system, the Army's 280-millimeter gun. When this shot was added to the program, some additional effects tests were scheduled to observe results of the low burst height, approximately 520 feet above ground. Since no gun-type assembly had been detonated since the Hiroshima bomb, the weapons development scientists had on this shot their first opportunity to study the nucleonic behavior and fireball configuration of such a device. Yield 15 kilotons. Unlike the situation with an implosion weapon, the scientists were here able to observe fireball growth from a body of fissionable material whose exact shape and dimensions at the moment of detonation were known. As scheduled, the military effects tests total well over 70 distinct projects under 9 major program headings. Headings which might in a sense be considered as signposts guiding us along our road. The road full of questions that we followed through Knothole, one of the biggest military test programs in our records. To begin with, we wanted more and clearer data on blast and precursor phenomena, and on the Mach stem, and the triple points path. We wanted enough data to predict what these factors, plus thermal and nuclear radiation, will do, of military significance, to any living being or object they can reach. These were the objectives of our road. We haven't the time to stop for a look at every signpost along the way. We'll just have to hit some of the high spots and new spots. A project, for instance, that didn't use a new technique, but that hadn't been covered in previous report films, had for its aim to measure free field blast pressures in regions of concern to delivery aircraft, and to determine the triple point height in at least one location. 2 B-29s did the muscle work on the job. Just before shot 9, they dropped 14 canisters in the target area, timed to be hanging on their parachutes at burst time and a long line some 5,000 feet high and spaced out to nearly 7 miles from the burst point. Each canister telemetered its altitude and surrounding air pressure to a ground station tape recorder. The tape also marked time of burst and time of shock arrival at the canister. The close-in canisters each received 2 kicks, one from the incident wave and one from the reflected wave. Farther out, each canister received a single kick from the Mach stem, indicating that the triple point where the 2 waves merge had sliced up through the canister line at a distance and altitude that we could compute from the recording tapes. In the nuclear radiation program, particular interest centered on Shot 10's neutron flux measurements, the first ever made on the detonation of a gun-type assembly. Gold, tantalum, and sulfur threshold samples were used to detect neutron energy levels from thermal to around 10 million electron volts. The total flux per kiloton was the highest ever observed, running 10 to 30 times as high as the implosion shots 8 and 9, and extending the median lethal radiation range some 600 feet. One novel feature of Upshot Knothole was the first use of drone aircraft on a continental atomic test. Navy AD-2s were instrumented for blast and thermal radiation response and were flown at near critical distances from several bursts. Results indicated that comparatively moderate thermal inputs may seriously reduce the blast resistance of some aircraft components. Standard blue aircraft paint proved clearly inferior to white or unpainted metal surfaces for protection against destructive thermal effects. Similar flights by manned and instrumented Air Force B-50s and a B-36 gave structural response data needed to establish minimum safe operational parameters for high-performance bombers. Other bombers from the Strategic Air Command flew in with the drop plane, testing techniques for obtaining yield, height of burst, and ground zero location, the 3 essential parameters of IBDA, indirect bomb damage assessment. On the biomedical program, Air Force QF-80 drones instrumented to measure gamma radiation and with test animals aboard were flown through atomic clouds at 30,000 and 32,000 feet. They were each controlled by primary and secondary motherships, and manned fighter escorts stood by to shoot down any drone that malfunctioned. These tests indicated that personnel of pressurized aircraft passing at 400 knots through a cloud at least 4 minutes old from a weapon of less than 30 KT would receive an external dosage of less than 50 Roentgens with a negligible respiratory hazard. On the thermal effects program, one project concerned parked aircraft and aircraft components, an extension of previous tests. New data were obtained on structural weakening from thermal inputs too low to cause visible damage. Cloth thermal shields were proved to have considerable value in reducing damage to parked aircraft. Some aircraft fabrics were destroyed at levels as low as 2 calories per square centimeter, while magnesium sheet and foil-covered panels were undamaged by 20 calories. It was also found that strong tie-downs may protect aircraft parked nose-on to the blast from much of the damage that will occur if the plane is unmoored and free to lift and roll. But for side-on or tail-on orientations, the tie-downs may actually increase damage. Another important section of the thermal program was a study dealing with normal city vulnerability to fire started by atomic weapons. 3 cubicle houses, 7,700 feet from zero, were erected for one phase of this study concerned with exterior kindling fuels. The first house has a clean, safe yard, but dry rot is working in the unpainted siding. No rot here, but toys, weeds, and trash against the fence. A clean yard, painted fence, and maintained siding. Number 9 goes off. 13 calories per square centimeter. Overpressure, 3.5 pounds per square inch. Time sequence photography shows the results. Destruction on the right from the yard trash would set fire to the fence. On the left, rotted wood in the siding was the ignition point. Sound painted wood and a clean yard allow the center house to survive. The fire hazards in these projects are not unusual either. 6 big American cities were inspected to ensure that representative conditions were tested. Conditions which suggest that a bomb of even this nominal power could start more than 100,000 fires over 25 square miles of urban area. Our next thermal project run on Shot 10 required a new instrument line east from Ground Zero, roughly opposite the main blast line, equipped with thermal recording devices and with blast gauges at 0 and 10-foot heights. The first phase, designed to find out how much protection white smoke would give against thermal flash, employed a standard oil fog over a portion of the new line. In theory, this smoke would scatter and reflect fireball heat. This was a small-scale experiment, but evaluations have indicated that attenuation of radiant energy approached 99%. To explain the second phase of the project, employing black smoke, we must go back to Tumbler Snapper. On the low-altitude burst of Tumbler 4, high-speed cameras recorded a phenomenon never noticed before, a shock wave preceding the main shock front. Here it is again. This precursor wave, as it was called, registers on blast line instruments with a pressure time graph of this type, showing a considerable climb and duration before arrival of the main shock front. A normal shock wave with no precursor is quite different, hitting the instruments with an instantaneous pressure jump. The mechanics of precursor development appear to be these. A weapon bursts, and thermal radiation creates an intensely hot ground layer of air, a layer filled with dust from what is called the popcorning of the hot ground. Milliseconds after the thermal flash, the incident shock wave reaches the ground and expands, trailed outward by the usual reflected wave. Then a new wave, the precursor, begins to build out from the base of the incident wave, racing ahead through the heated air layer. An intense dust cloud follows closely, rising initially to about 50 feet and later to several hundred feet. One important effect of the precursor is to lower peak static pressures without a corresponding reduction of dynamic or wind pressures. The precursor builds steadily in height, but does not seem to inhibit formation of a Mach stem, though exact dimensional relationships are uncertain. Eventually, running into cooler regions, the precursor slows and is overtaken by the Mach stem. From that point on, the blast wave structure is normal again. It should be emphasized that a precursor can form only if the ground air layer is sufficiently hot. So if height of burst is increased, yield must be increased. Without the yield increase, the ground air will be too cool for precursor formation, as was the case on Shot 9, our first effect shot, 26 KT at 2,400 feet. Shot 10, 15 KT at only 500 feet, developed a strong precursor. It was on this shot that we ran the smoke experiment. A carbon black smoke was established over nearly a mile of the new instrument line. We expected that the top of the black smoke would absorb thermal energy and produce an extra hot layer well above ground, possibly generating a controlled super precursor at that height, or in some other manner reducing blast effects on ground targets. The experiment was handicapped to an unknown degree by wind billowing the smoke up to 300 or 400 feet, modifying the planned geometry. As it happened, the ground-level precursor which developed under the smoke was stronger than the one in the clear, although it extended only half as far before decaying to a conventional blast form. This test was not conclusive as to the effects of a heat-absorbing black smoke on blast. A further precursor study was set up to determine whether ground surface heating from thermal flash could generate a shock wave before arrival of the normal shock front. Panels 10 feet square, faced with variously heat-absorptive and reactive materials, were tilted for maximum exposure to the thermal radiation of the two effect shots. Post-shot study of the gauge records showed no clear evidence of thermally induced shock waves. We come now to the biggest program, the primary reason for Shot 9, the first effect shot. The biggest program in sheer volume, in theoretical predictions confirmed or refuted, and in the mass of empirical knowledge gained. 28 separate projects came under this heading, beginning with basic measurements on simple cylinders and rectangular concrete slab structures in a number of orientations. These passive targets, heavily instrumented, were not designed for response by displacement, but only to record shielding and loading factors at various heights and aspects. The findings of this important job can now be extrapolated for prediction of blast loading on a great variety of targets without direct testing. We begin to bump into the precursor again. A truss bridge section 2,300 feet from zero. Shot 9, 26 KT, 2,400 feet high, produced a small permanent set in the top chord with an overpressure of 11.5 pounds per square inch. But the mock stem had not formed to reach the height of the bridge. 8.5 pounds did this on Shot 10, 500 feet high, 15 kiloton yield, with a precursor blast wave and a mock stem already higher than the bridge. Apparently, for wind or drag-sensitive targets of this type, a low burst is more damaging than a high burst at similar peak pressures. A test of Army prefab Bailey bridges. Shot 9. 4,100 feet from zero. Essentially undamaged, the bridge slid back on its piers as expected, moving 43 inches from a peak pressure of 8 pounds. 9 pounds from Shot 10 hits another bridge. Movement out of all proportion to that caused by almost the same static pressure on the first shot. Army equipment, which included 54 trucks and jeeps, was exposed to Shot 9 pressures ranging up to 21 pounds to the inch. Thermal input reached 130 calories per square centimeter. Damage was generally moderate, as expected. All but 2 vehicles, one with burned tires and one with a missile-punctured radiator, could be driven away under their own power. For Shot 10, Army tanks, artillery, and 22 trucks were exposed to pressures expected to range from 3 to 55 psi. Once more, damage was much greater than expected. Equipment was not merely overturned, but often torn to pieces or hurled great distances, at overpressures from which no such effects were predicted. Pressures which had done negligible damage to identical items on Shot 9. Obviously, Shot 10 was handing out surprise data. It was evident that our old static pressure criteria were not valid for predicting damage to wind-sensitive targets in the precursor region of low bursts. Not only were there violent high-frequency pressure fluctuations in this region, but the precursor static pressures no longer had the same relation to dynamic or blast wind pressures found in a normal shock wave. Standard command posts, foxholes, and machine gun positions were located on Shot 9 at 600, 800, and 4,000 feet from zero. Overpressures 8 to 22 pounds to the inch. General analysis indicated that cover-supporting timbers began to fail at 8 psi, while revetment stood up to around 20 pounds. Conventional sandbags tended to catch fire and spill their contents. One interesting finding was that foxhole covers can greatly reduce inside pressures, which may otherwise build to twice the outside pressure. Field hospital installations were displayed for Shot 9 at ranges around 4,400, 9,000, and 15,000 feet, in both above ground and dug-in positions at each location. Radiology sections, operating rooms, pharmacy tents, all complete and ready for use. 38 calories per square centimeter. £8 pounds per square inch. Operationally, a complete ruin, although a few items of equipment were salvageable. Missile hazard was unquestionably heavy. The 15,000-foot installation, around 1 1/4 pounds pressure. Damage limited to collapse of the above-ground tents. A significant finding of these tests was that considerable protection to personnel and equipment would be afforded by revetting field medical installations. 6 Marine LVTs, landing vehicles tracked, at distances from 800 to 4,500 feet from zero, with pressures reaching 22 psi, 2,400 feet, overpressure 11 pounds. Damage was light on all vehicles. On Shot 10, the same vehicles varied from 1,000 to 3,450 feet from zero, pressures running up to 47 pounds. Shot 10 damage was again unexpectedly heavy as compared with Shot 9, with 1 vehicle destroyed and 3 severely damaged in the precursor region, which on this shot extends out to around a half mile from ground zero. These tests suggest that normal shock waves from high bursts will damage LVTs only moderately up to 22 psi, while low bursts will do severe damage above 12.5 pounds. Curtain wall panels on a series of concrete test cells, some with window openings, some without. The panels were constructed of various masonry materials such as brick, cinder block, clay tile, and combinations of these materials. Similar variety went into roofs and interior partitions. On Shot 9, 4.5 pounds overpressure does this, 6,700 feet from zero. 7 pounds here, 4,400 feet range. Unreinforced brick stood up fairly well, though cinder block and transite shattered. Walls with 20% window opening showed much greater blast resistance than blank walls, though damage to interior partitions was high. 3 frame structures with windows and skylights containing various types of glass and plastic glazings were set up at 7,600, 12,500, and 20,000 feet from Shot 9. Pressures were 4 psi or lower. A few conclusions that can be drawn now are that 1/4-inch clear plastic shattered least of the material tested. 1/4-inch wire mesh was the largest mesh effective in reducing interior missile hazard. Exterior jalousies were worthless, and explosion hardware has very limited usefulness and may even be disadvantageous. Signal Corps placed radial and transverse pole lines, underground wires, and aluminum towers at different distances to test damage effects and determine time required to restore communication facilities. On Shot 9, pressures of 7 to 9 psi knocked down the transverse pole lines at 3,500 and 4,500 feet and partially destroyed lines at 5,500 feet in the 5-pound region. However, radial pole lines end on to the blast were almost undamaged. Similarly, towers at 3,400 and 4,400 feet were knocked down, and the one at 5,400 feet heavily damaged. At 6,400 feet, the top section of this 240-foot tower was made unsafe by 4.5 psi. Shot 10 damage to these installations was much heavier. The blast winds destroyed even the radial pole line to 2,500 feet, with static pressures by which it was undamaged on Shot 9. Air Force, Marine, and Quartermaster POL installations were given extensive testing. The major items were 5 and 55-gallon drum stacks, bulk storage tanks, and various subsidiary items such as can cleaning, metering, filtering, and pumping equipment. In general, Shot 9 damage was light or insignificant. There were minor gasoline fires. Drum and can stacks were scattered slightly in the maximum pressure areas, around 16 psi. 2 collapsible 900-gallon tanks were ruptured by 11 pounds at 2,600 feet. On Shot 10, results were unexpectedly violent. All stacks disintegrated, with cans and drums thrown hundreds of feet and left flattened or badly crushed. All marine fuel handling equipment was destroyed except 1 collapsible tank. Almost complete destruction occurred at better than 2,000 feet, at the same pressures that did trivial damage on Shot 9. A study of tactical importance. 145 ponderosa pines set in concrete, approximately 6,400 feet from Shot 9's 0. Instrumentation was thorough. A few major types being pressure gauges at 3 heights, time recording anemometers, pitot-type dynamic pressure detectors, and snubber wire arrangements to measure deflections. Pendulums were substituted for the lollipops of former operations to provide mechanical simulation of tree response. As on many of these projects, camera stations were set up to provide high-speed motion picture coverage of blast effects. Thermal input, 18 calories per square centimeter, resulting in only mild char on tree trunks, since the normal ground litter that will ignite at around 3 calories was lacking. Static pressures around 4 psi. Post-blast survey indicated that approximately 20% of the trees were broken, and the missile hazard from falling trunks and limbs would be substantial. There was scant reduction of static pressure inside the stand, but a 20 to 40% reduction of dynamic or drag pressures. Thermal shielding proved excellent, with negligible penetration beyond the 4th row of trees. 16 items of Army rolling stock were exposed on Shot 10 only. A 45-ton diesel locomotive, 1 riveted and 1 welded steel tank car, 13 boxcars loaded and unloaded of various types, 6,600 feet, 2 pounds overpressure, 4,400 feet, 4 psi, 1 empty boxcar turned over, 1 loaded car damaged, 3,400 feet, 6 psi. Boxcars damaged or overturned, 2,800 feet, 7.5 pounds, 1,850 feet, 9 pounds, 1,500 feet, before being hit by 13 pounds to the inch. And here's the same view afterward. The frame of one of those tank cars was thrown against a building 200 feet away. A tank car body went 1,200 feet. The whys and hows of these excessive damage effects at static pressure levels where no such results were anticipated will require further study, as will the mechanics of precursor development over surfaces less suited to the development of heated ground air than the Nevada desert. While to date these damage effects have been observed in the precursor, it does not follow that attack conditions should be chosen to maximize precursor formation. Such effects may be characteristic of any low burst, without regard to precursor phenomena. Although high bursts are still required for optimum damage on many important targets, the tremendous destructive force of a low burst has brought about an interim restatement of damage criteria for drag-sensitive targets, and was the most important single finding of the military effects tests of Operation Upshot Knothole.
Five, 4, 3, 2, 1.
One American town looks like any other when you see it from an airplane window. Trees line the quiet residential streets, and there's usually a highway running through to an industrial area where many town people work. But in every town, you'll find houses like this, run down, neglected. Trash and litter disfigure the house and yard. An eyesore, yes, and as you'll see, much more. A house that's neglected is the house that may be doomed in the atomic age. What would happen to such a town if it were on the outer fringe of an attack directed at a nearby city? We can answer that question, in part at least, even though it hasn't happened yet. A series of civil defense tests were made to discover the effects of atomic heat on American homes. I am going to show you how protective measures can help guard your home against the heat effects of an atomic explosion. This is the Nevada Proving Ground, where tests were made on miniature houses and various stages of upkeep, inside and out. These tests were also made on common fire hazards like dead grass, old leaves, discarded newspapers, and fence structures. Here are 5 fences placed far enough from the explosion that they could survive the blast. The fences in the middle are built of decayed wood. Dry grass and litter simulate conditions you've seen in too many alleys and backyards in slum areas. The trash, litter, and dead grass are perfect kindling for the unprotected and unpainted wood of the fence itself. The moments tick away as we await the bomb and the fireball. The light flash and the heat or thermal wave, then the blast wave. You'll remember the 3 middle fences are built of rotten wood, unpainted and surrounded by trash. They are immediately ignited. The 2 outer fences, without litter, are slower to ignite. Decayed, combustible wood surfaces like these fences are readily ignited by heat flash. Likewise, some types of interiors are easily ignited. This will be demonstrated in the next test. Here are 2 miniature frame houses, identical in structure, both in good condition and well painted outside. Sturdily mounted cameras in front of the houses are to record the effect of heat flash. Large windows purposely expose the interiors to the flash. In the house on the right, all the earmarks of untidy housekeeping. Newspapers and magazines lying about, and cluttered tables. Now the house on the left, identical to the other, but spick and span. Trash has been thrown away. Tabletops are tidy. 2 homes, one a fire trap, even under ordinary conditions. The other cleaned up and fresh with better, safer housekeeping. Both ready for the test bomb. The light flash and the heat wave, then the blast tears away part of each roof. Let's see it again in stop motion. First, the light flash and the thermal or heat wave that only chars the painted outer surface of both houses. Then the blast. The cluttered room of the house on the right bursts into flame. In a few moments, the interior is completely ablaze. The fire that started inside spreads rapidly to the house itself, although the house on the left still shows no exterior flames. Now the house on the right burns as fiercely as if it had been deliberately fired with kindling. The lack of fire-safe housekeeping has doomed this house to destruction. In the other house, with its better, safer housekeeping readily extinguished afterward. Damage? Yes, but the house still stands. One house standing, one house leveled, both painted and cleaned up outside. Identical houses except for inside conditions and housekeeping. Now, our third test. 3 identical miniature frame houses, each with varying exterior conditions, all the same distance from the point of the explosion. The house on the right, an eyesore. But you've seen these same conditions in your own hometown. Old, unpainted wood. And look at the paper, leaves, and trash in the yard. In a moment, you'll see the results of atomic heat flash on this house. The house on the left, typical of many homes across the nation. Heavily weathered, dry wood in run-down condition. This house is the product of years of neglect. It has not been painted regularly. It's dry and rotten. A tinderbox ready to turn into a blazing torch. The house in the middle, in good condition, with a clean, unlittered yard. The exterior has been painted with ordinary, good quality house paint. Light painted surfaces reflect heat, and the paint also protects the wood from weathering and moisture damage. Let's watch the test now and see what happens under atomic heat. See it again in stop motion. The light flash, the heat wave, and clouds of dust. Keep your eye on the house on the right. Notice how the heat wave affects it. There's the fire starting in the trash surrounding the house. Now it spreads to the house itself. In a moment, the blast wave, and here it comes. The house on the right is the first to ignite. The trash serves as kindling for the dry, weathered wood. The house on the left smolders for a few moments. Looks almost as if it will not burn, and then bursts into flame. The house on the right continues to burn. 2 houses are a total loss, but the well-kept and painted house in the middle still stands. Which of these is your house? This one? The house on the right, dilapidated with paper, dead grass, litter everywhere. The house on the left, unpainted, run down, neglected. Is this your house? The house in the middle, cleaned up, painted up and fixed up, exposed to the same searing atomic heat wave, did not catch fire. Close examination revealed only a slight charring of the painted outer surface. Yes, the White House in the middle survived an atomic heat flash. These civil defense tests have proven how important upkeep is to our houses and towns. Now it's up to us, the people, to take decisive action. All right, you say, what can I do about it? What can my community do? All over America, towns and cities are organizing local cleanup, paint-up, fix-up campaigns. Boy and Girl Scouts and school children of all ages are told how they can help by organizing teams to clean up alleys and backyards. See that you help by removing all of the litter, junk, old newspapers, and trash. They collect and pile up. Your community needs this help. Do those long-delayed repair jobs now. Trim your shrubbery and trees, weed and plant flowers. Keep your block cleaned up. Beauty, cleanliness, health, and safety are the 4 basic doctrines that protect our homes, our cities. You've seen the tests. You know the story. Join up with your friends and neighbors for a better, safer community. It's also good civil defense, which is everyone's responsibility. The dingy house on the left, the dirty and littered house on the right, or the clean white house in the middle. It is your choice. The reward may be survival.
In the picture we are about to see, we must remember that the explosive power of atomic bombs used in this test was in the kiloton range. The explosive power of today's hydrogen bomb is measured in terms of megatons. What does that mean to us? It's a matter of practical application. It takes 1,000 kilotons to equal 1 megaton. And by applying the scaling laws, the proportionate comparative effects of a larger bomb can be determined. The A bomb exploded here was rated at approximately 30 kilotons. For comparison, let's use a 20 megaton H bomb. The 20 megaton bomb, therefore, would be 667 times as strong as a 30 kiloton bomb. The relationship between distance for any given pressure and the size of nuclear weapons follows the cube root scaling law. So theoretically, a hydrogen bomb of 20 megatons at approximately 8.5 miles would have about the same destructive power as an atomic bomb of 30 kilotons at 1 mile. In this test, many of the structures were approximately 1 mile from ground zero. In the case of a 20 megaton H-bomb explosion, most of these structures undoubtedly would be obliterated. And actually, at a distance of 8.5 to 9 miles from ground zero, with the longer duration of blast pressure, we could expect to find conditions even more severe than those at 1 mile from ground zero in this test. This atomic test, although depicting the severe effects of a nuclear weapon, does not reflect the extent and severity of destruction that result from a nuclear weapon in the multi-megaton range.
Here at the Atomic Energy Commission's Nevada test site, I covered the story of Operation Q, a program to test the effects of an atomic blast upon the things we use in our everyday lives.
Operation Q, the atomic test program of the Federal Civil Defense Administration, as seen by June Cowan, reporter.
I had to see Operation Q through many eyes, not only my own, but as a reporter through the eyes of the average American man and woman. I arrived at Civil Defense Headquarters the day before the explosion was scheduled to take place. and checked in at once with the official who was to brief me about the test. To give me a perspective of the entire layout, a member of the Civil Defense staff showed me a carefully prepared model of the site. The scope of the test and the detailed care with which it had been planned amazed me as I listened to the explanation.
We begin with the question of shelter, for shelter might save our lives if we were far enough away from ground zero. If so, what kinds of shelter are effective? Several kinds are to be tested, from elaborate industrial shelters to the box-type shelter in the corner room of a basement. This type would give more room for a family, especially if it were necessary to remain there for several days. In this frame house without a basement, at the 4,700-foot line, we will test a bathroom shelter built of reinforced concrete. The entrance door and outside window covering are designed to resist blast.
I asked about the possible loss of utilities and what this would mean to survivors. No electricity for running a home or an industrial plant.
Loss of power may be one of our biggest problems after an attack. Power poles, power lines, pole transformers, and complete substations are to be tested by the Edison Institute. How will they withstand this blast? How long will it take to make repairs? How soon can service be reestablished? These are things we hope to learn from the test. One complete transformer substation has been erected relatively close to the shot tower. A second substation and power lines have been placed at a much greater distance from the tower.
Thinking about news during an atomic attack, I asked about radio towers.
Two kinds are to be tested. One tower is self-supporting without guy wires. The other has supporting cables. Both types are very common. Nearby, a complete radio transmitter will actually broadcast from tape before the shot to be picked up by radios in the test houses. Both liquefied petroleum and natural gas facilities will be tested. Will the fittings and connections stand the test? Will there be fires? All equipment is installed and checked by technical experts from the LP Gas Association and the American Gas Association. An 18,000-gallon supply tank, partially filled with propane and complete with feed pipes. A weighing and storage house and delivery platform have been erected on the test site.
I was anxious to learn all I could about the various types of houses to be tested.
5 types are prepared for exposure to the blast and heat of this atomic explosion. First, a single-story frame rambler without basement built on a concrete slab. Second, a 2-story masonry with basement constructed of brick backed with 4-inch cinder blocks. Third, a house of 8-inch concrete blocks reinforced with steel. The 4th type is a single-story rambler made of precast lightweight concrete. Walls and roof panels were joined by welding steel lugs. The 5th, at the 5,500-foot line, is a redesigned house similar to one previously tested. This new design provides additional strength at a cost increase of approximately 10%. That's the real purpose of testing these houses, to find their weak points. Through the cooperation of the furniture and appliance industries, household furnishings were installed in the houses. Mannequin families supplied by private industry are to represent Mr. and Mrs. America.
Interior home furnishings donated by industry are complete in every detail. I looked at the mannequins sitting about so indifferently. Naturally, I was very interested in preparations for the testing of textiles and synthetic fabrics.
Rows of mannequins were set up in the open facing the blast. Each item of clothing and each color had been carefully selected to give much needed survival information.
I was especially interested in the food test program. Canned and packaged foods are to be tested. As a mother and housewife, this appealed to me. I had several questions to ask. Would food in the average home be safe to eat after a blast?
Food testing in Operation Q is planned to answer this and other vital questions. Some foods are to be tested in the house, stored in the usual way. Other foods, including fresh meats, butter, and similar perishables, are to be tested just below the level of the ground at 3 positions along the main test line. This will expose the food to high-intensity radiation without risking destruction of the containers. Test items include sterilized foods packaged in cartons, metal, and glass. All will be exposed according to plan to give us the most survival information.
The night of the actual explosion, or rather early in the morning, came at last. On Media Hill, television equipment was ready to bring the test into homes from coast to coast. Reporters, commentators, military and civil defense observers all had a purpose: to study the results of this explosion. At a position a mile forward from Media Hill, the Civil Defense Field Exercise Group had assembled with their equipment. A small group of civil defense volunteers were to occupy a trench relatively close to ground zero. On Media Hill, where I remained, there was hot coffee, last-minute briefings, and more waiting. But it seemed no time at all before the loudspeaker warned,
H-minus 1 minute. Put on your goggles. Observers without goggles must face away from the blast.
On the silent desert, the test objects waited.
H-minus 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Elapsed before we were permitted to view at first hand the results of the explosion.
Let's see how the blast affected the houses. This is what remained of the masonry house that was not reinforced. This is the house constructed of reinforced concrete blocks after the explosion. Although the redesigned 2-story frame house was severely damaged, the structural improvements had strengthened its resistance considerably. As seen here, although basement shelters offered some degree of protection, they cannot be depended upon completely in potential blast areas. The reinforced bathroom shelter was standing intact beneath the ruins of the house, so this type also offered some degree of protection. The upper section of one unguided radio tower collapsed from the tremendous force of the blast. The guide tower was slightly twisted by a power pole which fell across one of the guy wires. Within the concrete radio house, equipment had been shaken up. But as soon as power was restored, the transmitter resumed broadcasting. The 18,000-gallon tank of liquefied petroleum gas was undamaged. Tests showed that even the connections were intact. The weighing and storage house was scattered across the desert, but the consumer-sized tanks were unharmed. Power lines and transformers suffered some damage, but most of the power poles were still standing or could be repaired. The power substation was not seriously harmed. Edison Institute personnel tested all lines and found the station to be operative. The food and cases of canned goods were taken away for laboratory tests.
Do you remember this young lady? This tattoo mark was left beneath the dark pattern. And this young man, this is how the blast charred and faded the outer layer of his new dark suit. During all this activity, the mass feeding group was improvising to feed the test observers. I particularly remember some roast beef. It was done to perfection and roasted in cans which could have been salvaged from demolished buildings. I watched the people eating and realized that mass feeding is an important job in civil defense. I took a last look at the debris and devastation. This time it was only a test, a well-planned test, not a real attack. It was a test of the things we use in everyday life.
Many lessons were learned from this test that affect civil defense planning. And it must be borne in mind that multi-megaton weapons would result in much greater damage over a larger area. All these factors must be considered as we plan for the survival of our homes, our families, and our nation in the nuclear age.
My name's Conrad Steiner. I'm a doctor of medicine. Tonight's story has the title, Flash of Darkness.
Guardian of birth, healer of the sick, comforter of the aged. To the profession of medicine, to the men and women who labor in its cause, this story is dedicated.
Tonight's presentation, the field of emergency first aid. The object in point, an armband bearing the letters CD. The case in point, Conrad Steiner, MD, age 42, married, father of 2 children. Although seemingly in good physical condition, he's actually in very grave danger. The danger does not threaten him alone. It is a vicious, virulent disease which may very well destroy all mankind.
Dr. Steiner's office. Who's calling, please? Oh, yes, just a moment. Dr. Steiner?
Yes, Mr.
Telephone. Mr. Wilcox. He says it's important.
Hello, John. I see. Is this a test? All right, thank you. Miss Mitchell, have we got any patients that can't wait until tomorrow?
No, nothing very serious. Why, Doctor?
Well, don't alarm them, but send them on home as a yellow alert.
Practice?
I don't know. But send them on home anyway. I'll call Miss Steiner and then we'll get over to the warehouse.
Did you get Mrs. Steiner?
No, I just hope she didn't pick the day to go downtown shopping. Kids are all right. They're in school.
I sent the patients home, but they didn't like it. If this is just another test, you're going to have some pretty unhappy patients.
Well, they're going to have a pretty unhappy doctor. Let's go.
Sure good to see you, Ed. You can see how short-handed we are. Not much of a showing.
What is this, Harry? Another test?
You know as much about it as I do. Huh. Maybe Dr. Steiner has some information. Oh, Doctor.
Hi, Doc.
Hi.
What's the dope on it?
I don't know. I got the same phone call you did. That's all I know about it.
Huh? Mr. Sherman's pretty unhappy about my leaving the drugstore. Peak hour coming up and everything.
I had a patient in the chair when they called me. Already had the Novocaine in. Well, at least the tooth won't trouble him for a while.
I guess I'm a little excited myself. I forgot all about it. I've got a battery radio in my car. We should be able to get some indication from Conrad.
Well, I just wish they'd get this over with. I've got to get home and dress. My friend Mr. Harwood's having a big party tonight. It's his birthday. He gets awful upset when I'm late.
Honey, if they'd known that at headquarters, they'd never have called an alert. Doctor, did you remember to call your exchange?
That's no practice alert.
Sure wouldn't pull a red alert for a test.
Well, does that mean we're in war?
We're in something, honey.
What about that radio, Doctor?
No, we'd better get sheltered.
You mean this is all the air raid shelter we've got around here?
There's a bomb drop. They won't waste it on the suburbs. Probably drop it on the city itself. That's a good 14 miles away.
Well, you don't think this is just somebody's bright idea, do you? Some kind of super test or something?
Get out. That shockwave will hit any second. Come on, get out.
My God. My God.
Was it downtown?
Hit any closer, we wouldn't be talking about it.
My friend Mr. Harwood, his office is downtown. It's right in the financial district.
Let's wait for the all clear. There'll be plenty to do then.
I'll try control.
Good. Ed. It's 10 to 3 already. A lot of people up there are going to need help. Let's start moving these cases while we're waiting.
Okay, Doc, I'll try to find a couple of hands.
Zone 3. This is Wild. We're at the warehouse. Then we're short-handed. Send us every available man you can find, will you? Right. There'll be 2 trucks out right away. Morningside area was badly hit. Their alternate control headquarters is asking everybody for help. We'll check back for an estimate on the fallout pattern. Going to try Laura?
No, we'll keep the lines clear. She said she might go shopping.
Downtown?
I don't know. We better get moving. I'll check that battery radio in my car and see if it still works. We can't trust the mains up there. We better find containers and take emergency water up with us. Where have you been? It's been over an hour since we called control. They promised to send help. We're it. All right, let's load up. After 4, we got to be set up by dark.
Mobile first aid unit, zone 3. We got orders to set up in the Morningside Armory. Can't go any farther. The fire lines aren't stabilized. We've been 3 hours coming east 5 miles. This is the end of the line for now anyway. Feel that wind? The firestorm's so hot you could cook a steak at the next corner. Is that a school over there? Is it safe? Radiological says the whole area's clean. I don't know if it's had a structural check, but it looks okay. All right, that's where we set up. How about the water main? Gone. Everything's down. Power, gas, phones. All right, let's go!
much, but it's home. It's in better shape than I thought. Miss Mitchell! Got enough room to isolate the worst cases. Use the auditorium as a holding area. Mitchell will set up surgery down at this end.
Harry!
Yeah? Just stopped the police car outside. He's got a radio.
Well, ask him to call control of this zone. Tell him where we're set up. Tell him we need help. A lot of it. Right away. Tell him we need stretcher bearers.
We need water.
Right!
We'll have to get these desks cleared out. Move in the supplies. Use the desk to build a fire. Get water boiling for the instruments. Come on, let's do it.
I better change to my uniform.
Yeah, that'd be a help.
Civil Defense Headquarters for this region has just released the news that Ground Zero was approximately 1 block east of the Union Station. Emergency aid is being rushed into all devastated areas in the state. No reports are available at this time as to total damage of the nationwide attack, but the enemy is reported to have paid heavily in aircraft loss. This is Conelrad. Keep tuned to this frequency. Obey the instructions of your wardens and civil defense workers. Emergency aid is being brought in. Keep calm.
They've established Ground Zero, Union Station.
There won't be anything at all left in the downtown area, Mitchell.
Broadcast over Conelrad. Obey the instructions of your...
Any word about your wife?
What happened, son?
There was a whole lot of preserves Mom had in the cellar. This glass went flying all over the place.
Pretty lucky at that. It's just scratches. We'll have you fixed up in no time at all. Mitchell, soap and water, methylate. No dressing. You go with the nurse, son.
Doctor, will you fix up my brother? He says he can't see. I told him to stay inside, but he ran up the cellar steps. He wanted to see it. After the flash came, he fell back down. Then when I went over to see him, that's when the glass hit me. Almost our whole house fell in.
Was he looking at the blast?
He threw up 4 or 5 times. The fire engine gave us a ride back. And he was sick all the way.
Mitchell, decontamination and take this boy down to isolation. You can stay with your brother if you like, son.
Can you fix him up?
Well, he's a pretty sick boy.
I'd sure like to call my mom if I could. She works downtown. Do you know if there's a phone I could use, Doctor?
Well, not right now. Maybe a little later. You go with the nurse.
Doctor, that little kid, is he going to be blind?
I won't bother him for long. The amount of radiation he's taking, he'll be dead.
Doc? That's all I got wrong with me. Can you tie it off? I notice you're pretty short. You got him stacked up way into the street. Can you use some help?
All we can get.
Okay, you can count me in.
Thanks.